Hello, in this video we will talk about quarks, leptons, gauge fields and Higgs bosons in the context of Standard Model. Electron as a particle is known for a long time, and so was photon as the quantum of light, and also we know about the muon, then electron neutrino and the muon neutrino. However, today we will discuss about the complete spectrum of matter and force carriers included in the Standard Model. This is matter part 3/4. This sector is the matter part. This column is force carriers, which are gauge bosons, and this is Higgs. The main difference is that the matter part, they are fermions, they are spinors, they are spin half particles, and this column, they are vector particles, that is they have spin 1, intrinsic spin 1, and Higgs boson is a scalar particle, that is intrinsic spin 0. What are the other differences? Let us first look at the matter sector. Matter sector has quarks and leptons. These upper two entries are quarks and lower two entries are leptons. The difference between quarks and leptons is that quarks can respond to all four types of interactions, that is strong, weak, electromagnetic and gravitational, whereas leptons respond to three types of interactions. That is, they cannot respond to strong interactions, but they can respond to weak, electromagnetic and gravitational interactions. And sometimes we put this U and D or C and S or T and B in the form of a doublet. Nu E and E in the form of a doublet. These are weak isospin doublets. Here the upper member has weak isospin plus half and lower member has weak isospin minus half. Similarly here, weak isospin plus half for Nu E and weak isospin minus half for electron. The entries within these doublets U and D, they are spinors. That means they are spin half particles, which means that weak isospin and intrinsic spin, these are two different quantum numbers. Even though this is a doublet under weak isospin, each individual entry in this weak isospin doublet, they have intrinsic spin half. That means they have spin up and spin down components. Then there is these neutrinos, the three neutrinos. This is mass eigenstate, and these are Nu E, Nu Mu, Nu Tau, which are weak eigenstates or the flavor eigenstates. And mass eigenstate is a linear combination of flavor eigenstates. And we know that the time evolution, when we look at time evolution, we have to look at the mass eigenstate. When this mass eigenstate is evolving with time, these components, the Nu E, Nu Mu, Nu Tau, the ratio, that is this coefficient C1, C2, C3, they determine the amount in which Nu E, Nu Mu, Nu Tau are present in the mass eigenstate. And those ratios keep on changing constantly, which leads to neutrino oscillations. Nu E can oscillate to Nu Mu, can oscillate to Nu Tau. After a while, we will see this mass eigenstate will have different mixture of Nu E, Nu Mu and Nu Tau. Some Nu E has oscillated to Nu Mu and so on. And all three of them can oscillate among each other. Then this column, this is the force carriers or the gauge bosons. This is gluon, which is the force carrier of strong interaction. Photon, force carrier of electromagnetic interaction. Z and W boson, these are force carriers of weak interaction. And Z and W boson are massive. The mass is that the Z boson has mass 91.2 GeV and W boson has mass 80.4 GeV. But very early in the universe, they were also massless. When the temperature of the universe fell below 100 GeV, symmetry was broken and that has led to the masses of Z and W boson. And that same mechanism has also provided mass to the quarks and leptons. And this symmetry breaking is triggered by a vacuum expectation value of a scalar Higgs boson. When initially we postulated the existence of quarks, that is UT, CS, and TB, in the early 1960s, when the existence of quarks was postulated, many people thought that they are mathematical quantities. They do not have any physical significance. Later, in deep inelastic scattering experiments, mainly done by Kendall, Friedman, Taylor, and their collaborators, and they won Nobel Prize in 1990, provided the first convincing evidence of the existence of quarks inside nucleons. Nucleon, and there are quarks inside the nucleon, and we use a very high energy beam, electron beam, which can scatter the quarks inside the nucleon through the exchange of a photon. That is a electromagnetic scattering. So we have to look slowly, then we will understand. This is a space-time diagram. Time is going this side, space is going this side. This is nucleon, and inside nucleon there are quarks. And a very high energy photon is scattering, is moving inside this proton and scattering with the quarks. The quarks cannot come out of the nucleon. That is because they are not free. They are bound inside proton, but asymptotically they are free. Probe deep inside into the proton, then we will see these quarks are free. This is the electron. It will emit a photon because it couples to photon. It has electric charge, so it will couple to photon. And this photon in the other end, it will couple to the electric charge of the proton. This electron is scattering with this proton after a while. That means this is a time interval of electromagnetic interaction, delta t. This is typically 10 to the power minus 15 seconds. In the other end, this high energy photon provides sufficient energy so that it will break this proton, and this proton will be fragmented into partons. Partons means the parts, and after a while, after a very short time, that is, this is delta t for strong interaction, that is about 10 to the power minus 24 seconds. After a while, these partons, that means these fragments, will be hadronized, and final state will consist of these hadronic jets and a lepton. This lepton and this hadronic jet. An initial state is the electron and a proton. And this is electromagnetic scattering, and here we have fragments of the proton, and then after a while those fragments will hadronize and form jets in the final state. So this is time direction and this is space direction. That means this electron is coming in the positive x direction and returning in negative x direction. Proton is coming in the negative x direction, and these jets are scattered in all possible directions. The final state consists of lepton and multiple hadrons with at least one baryon to conserve p quantum number, because there is at least one baryon which is coming. So final state should have baryon number 1. And finally, we should understand this very carefully, that because the quarks do not have further substructure. These quarks are elementary particles. That means the scattering of electron with quarks, that will be elastic scattering. That is because quarks do not have further substructure, they scatter elastically, even though the nucleon as a whole scatter inelastically. And the proton has broken to fragments, so that is not a elastic scattering. That means proton is scattering inelastically, even though quarks are scattering elastically. So that is the essence of deep inelastic scattering, which has provided the first convincing evidence of the existence of quarks, means elementary substructure inside nucleons. So I suppose that is all for today's discussions, and thank you for watching.